Hello and welcome back. This is one of my favorite slides. I went out to the internet and I said, oh, signs about nuclear and radioactivity or something like that. And these are the images that came up. I mean, they don't look pleasant. My favorite is that one right here, the guy with whatever those things are going through and doesn't look at all pleasant. So everybody has this idea that radiation, bad. All radiation, bad. So let's kind of explore that and see where it came from. One of the things I asked you at the beginning of this chapter, if you watched from video number 1, if you're just kind of jumping in, hi, there's other videos. All right, so if you've just watched from video 1, you know that I asked you at the beginning, how much are you right there sitting in that chair or whatever you're doing, on a bus, whatever, watching me, hi, person next to you, how much radiation are you hit by? How much radioactive decay particles from actual like radioactive things falling apart, alpha particles, beta particles, are you being hit by at any given moment in time? And you made a guess, and I hope you remember that guess because I'm about to tell you the answer. And I did a lot of work to look up this answer. I made actually a bunch of calculations and looked up data. I didn't just kind of come this off the top of my head. Unfortunately, I didn't write down my method, so I can't actually reproduce my calculation without starting over, and that was a lot of work, so I'm not going to do it. So this is probably a rough estimate, and I can't prove it to you, but I think it's right, and I'm pretty darn sure it's right, or at least fairly close. But you, sitting there, right there in your chair, are being hit by 90,000 particles of naturally occurring radiation every second. Boom, 90,000, boom. 90,000, boom, 90,000, boom. Wow, that's a lot, right? In the time it takes me to say this sentence, I might be hit to close to 1 million particles of radiation. In a day, it's going to be a huge number. We are constantly being bombarded with radiation. How is one to survive? But the answer is we do. Our bodies are naturally resilient to most forms of radiation unless we get too much of them or it hits in just the wrong spot. So we'll talk about different forms of radiation. So yes, we do get exposed to quite a lot of radiation over time. Now, we sometimes do it on purpose. So right here is medical radiation. So somebody getting an iodine-131, they're checking the thyroid. I don't know much detail about the thyroid except it's a butterfly-shaped organ and it does something about hormone controls and things like that. I should probably learn more about it since there's someone in my household who has hypothyroidism. But that's about all I know. But if they're trying to check how your thyroid's working, one of the things the thyroid does naturally is take in iodine. And so they give you a cocktail of iodine-131, which is a radioactive isotope of iodine. And they say, hey, drink this or inject it or whatever they do. And then they take a scan of you. And that thing is sitting there in your body and it's emitting radiation. Now, if your thyroid is working normally, it's going to take in some of that iodine. And so your thyroid is going to be somewhat radioactive. If your thyroid is hyperactive, it's going to take in a lot of that iodine and your thyroid is going to be very radioactive. And if you have hypothyroidism, it's not going to take in much, and your thyroid's going to be much less radioactive. And so they can look at those scans and see if there's parts of your thyroid more, and figure out all sorts of neat things about how to best take care of you if you've got some thyroid issues. Now, that iodine-131 undergoes beta decay. So if we go ahead and take iodine right there, beta decay, if you remember, 0 minus 1 beta, which means what we have after that is 131.54, and if you look that up, that's xenon. So the iodine in your body turns into xenon, which is certainly not really a problem. It's one of the noble gases. In fact, most of it you end up peeing out, so you don't actually end up with radiation. But you also remember we talked about the half-lives here, right? This one has a relatively short half-life. Why? So that you're not walking around being a bag of radiation for the rest of your life, that eventually you pee it out, and even the stuff that stays inside of you naturally decays. All right, you can also get a PET scan, positron emission tomography. It uses fluorine-18, and if you know what a PET scan is for, it's mainly for looking for brain tumors, brain scans. So how easy is it to get things to go into your brain, right? If you drink something, you eject something, there's this thing called the blood-brain barrier that tries to prevent foreign things, foreign chemicals from going to your brain. So what do? We trick the brain. We say, hey, I know you don't want this radioactive fluorine, but do you know what you want? You want sugar. And so we attach this radioactive fluorine onto a sugar molecule. The brain says, sugar, I like sugar, takes it in. Now, what we're looking for primarily in these PET scans is cancer. And what is cancer? Don't get into the internet things about what cancer is, but it's essentially unregulated cell growth. Okay, whatever it is, it's unregulated cell growth, cells that are just kind of going. And if they're going, they need a lot of food. They need to be able to reproduce, they need a lot of food. And so if you have unregulated cell growth, those things are going to be taking in a lot of sugars, and you just radioactively labeled your sugar. And so now those areas of your brain that are overgrowing are going to be super radioactive, and someone looking at a scan of the stuff coming out can tell what's going on. Now, the fluorine-18 here, fluorine's number 9, positron emission, 0 plus 1, right? So when you're doing this kind of scan, you're actually looking for antimatter coming out of your brain. It's crazy, but that's what's going on. 0 plus 1, and then you get 18, 8, and it just turns into oxygen. Okay, so 18, 8 turns into oxygen. So we don't have to worry about the oxygen being in our brain, but we started off with that fluorine. So there's just a couple of medical applications, but that's when we do it on purpose. But I'm just saying, you sitting here in your chair right there, 90,000 counts of radiation per second. Where are they coming from? Well, let's take a look. So common sources of radiation exposure. And the dose over here is called millirems, right? A rem is a radiation equivalent in humans. It just says how damaging is this radiation. The bigger the number, the more damage it does. Now, it does take into account that alpha particles can kind of hit you and not much happens, but gamma can go all sorts of ways through you and cause all sorts of damage. So it takes that into account, right? So let's look. The ground. That stuff you're standing on is exposing you to 20 millirems of naturally occurring radiation every year. Air, water, food, 30. That's more than the ground. So instead of flying to try to get rid of that radiation, you should just stop eating, drinking. No, you can't do that, right? This is natural. The apple that you eat, radioactive. The water that you're drinking, radioactive. The cow, the burger, In-N-Out. I know if you're from California, you know what I'm talking about. If not, you probably don't. The burger that you're trying to eat, radioactive. The lettuce in there, radioactive. Why? Because it's naturally occurring. It's just out there. We talked about carbon-14, but there's all sorts of other radioactive isotopes of potassium and other things that just naturally occur in the world. Okay, so those add up to about 50 millirems per year. And then there's cosmic rays. And what are cosmic rays? That's just stuff coming from space, mostly from the sun coming down. Sun is a nuclear reactor. It's producing all sorts of nuclear waste and nuclear particles and energy and things like that, and some of them come down and hit you. Okay, so the sun, naturally radioactive and dangerous. Okay, here's the kicker. Wood, concrete, and brick. 50, right? So don't go into anything made of wood, concrete, or brick, which is like every building ever. So you can't avoid these things. You can't avoid completely being exposed to radiation. It's just not possible. And it's fine. Most of us live just fine being exposed to 90,000 counts of radiation per second. It's okay. Now, you don't want to go out and expose yourself to excess radiation, right? That's not bad. I mean, that's not good. You don't want to do that. Let's look at some of the excess radiation that you get. So here we go. The ground gives you 20 millirems of radiation. Medical chest x-ray gives you 20. Like, that's just the same as the ground. How about if I get a few chest x-rays just for fun? And it's just like, oh, I just laid down on the ground for a little while. Well, what's the difference? The ground gives you 20 millirems in a year, right? So that's an annual exposure. A chest x-ray gives you 20 millirems in faster than really fast. Those x-rays nowadays are crazy fast. And in fact, thank goodness to digital technology, they use significantly less energy and x-rays than they used to use, because the digital plates are so much more efficient at gathering it and analyzing it. So chest x-ray 20, dental x-ray 20, mammogram 40, lumbar spine x-ray 70, and my favorite, the upper gastrointestinal tract x-ray. And I have no idea why they included that one. Like, are people getting those every day? But my guess is why they included this one is because the highest number they could find. And they said, hey, look, 200, let's put that on the table. So that's a lot, right? That's more radiation exposure than all the other natural sources combined that you get in a year in one gastrointestinal tract x-ray. So if they're talking about, hey, can we do an x-ray for this? Can we do an x-ray for that? Overall, one x-ray is not going to be a huge additional exposure for you. But it's also, if it's not necessary, don't do it. I mean, somebody wants to do an x-ray just to see if, you sprained your pinky, but, it's going to recover either way and it's not going to change your diagnostic or course of action, then don't do it. But, if you need to do it, it's okay, because we've done a really good job of reducing the amount of radiation we're exposed to and those kind of things. What are some other sources? People worry a lot about nuclear power plants. Oh, that nuclear power plant, it's going to kill everybody. If they're working just properly, they expose you to roughly 0.1 millirems of radiation every year, compared to 20 for the ground. Air travel. Government conspiracy? No. The cosmic rays come in And what stops most of them is our atmosphere. So what do? We get in these little tin cans and we go on top of the atmosphere and expose ourselves to extra cosmic rays. So yes, you do get exposed to extra sources of radiation from air travel. Television, not so true anymore. True when a giant television like this big, and ended up having a glass tube this big, it used electrons, shot them at a phosphorus screen, occasionally produced an X-ray or two, and you'd get exposed to radiation. So when your mom said, hey, don't sit so close to the TV, she was actually right, because it would reduce your radiation exposure. But nowadays, go for it. Just like put your face right up there. Okay. Radon. Not too much if you're from the West Coast. We don't have a lot of radon in the West Coast. But if you're in the Midwest, there's a lot of radon, and also it's a gas, and so it sinks. So if you've got a basement and you're in the Midwest where there's lots of radon, and you've got a basement that doesn't have very good circulation, you're building up radon, which actually seeps naturally out of the ground. It's one of the products of uranium decay, and it's also radioactive. Not good stuff. But you know, a good fan, blow out your basement, and you're just fine. All right, so those are our natural and sometimes unnatural sources of radiation. Now, what does it do to us? Well, let's look at this one. This is what's called the LD50. This is the dosage of radiation it takes to kill about 50% of a population. And if you look, you can see who's going to survive the first nuclear war. Yeah, the bugs, primarily the cockroaches. They can withstand a whole lot more radiation. A human can withstand 500 rems of radiation before bad things happen. Well, let's look over here and be like, well, gosh, that gastrointestinal tract X-ray, that's 200, and we're getting awfully close to that amount of radiation that kills half of people. Well, you have to pay attention to units. The dose on the natural exposures and the radiation was in millirems. This is in rems, so these are 1,000 times bigger. So yes, you have to expose humans to quite a lot of radiation before half of them die, but there's what it is. But bacteria and insects, you have to expose them to ridiculous amounts of radiation before they die. And guess what? A good chunk of the food you eat has been exposed to that much radiation. Yeah, look up strawberries and radiation. But do you know what? I eat strawberries. Okay, why? Because the type of radiation they use is gamma rays, and gamma rays, very high energy, could produce very high rems, but it's just a beam of light. So when it's done, there's nothing left. It's not particles. It's not actually modifying anything about the particles in there. It's just exposing the bacteria to so much radiation that they can't live anymore and they die. Okay, so strawberries, spices. Look up spices and radiation. How do you think they make those spices last so long on the shelf? They radiate them like crazy in order to kill anything, especially fungus, that might grow on your spices. All right, so fun stuff. Nuclear fission and nuclear fusion. What are these? Remember, we talked about fission is breaking things apart, fusion, putting things together. Every single power plant you see out there in the world is a nuclear fission power plant. We're breaking things apart. Why aren't we doing that one where we put things together? We'll talk about it in a moment. But it produces a ton of energy, and what do we do with that energy? How do we turn that energy into electricity? Well, we harness the power of the atom, and then we boil water. Really? These things out here are just very big water boilers. Okay? Why? Because we use the steam generated to turn a turbine, which then generates electricity, turbine. Now, in order to boil the water again, we need to cool it down. Here's your cooling right there. That's why a lot of these power plants are built next to water sources. But if you don't have a water source, you make these large cooling towers that look very ominous, but literally there's just spirals of water and they're blowing other water across it to cool the water down. Now, this guy's operating your nuclear power plant. Good luck for you. Luckily, I've met some of the people who design your nuclear power plant. Those are really good people. All right, how does nuclear fission work in our nuclear power plants? Well, usually we're using an isotope of uranium called uranium-235. If you hit it with a high energy neutron, it turns into uranium-236, which is very unstable and essentially instantaneously decays into krypton-91 and barium-142, both of which are fairly nasty and decay into other very, very nasty things. So it makes a ridiculously awful cocktail of products out of it that we have no idea what the chemistry is or how to deal with it. However, since we saw such very large energies in our other thing, even though it makes a whole lot of energy and we don't know what to do with it, it also produces a very small amount of it, okay? But what else is produced? A ridiculous amount of energy, which we can boil water with, then 3 other neutrons. But what can those 3 other neutrons do? Well, each one of those neutrons can go then and hit a uranium-235 and make 3 other neutrons. And so you get this guy generating 3 neutrons, this guy generating 3 neutrons, and this guy generating 3 neutrons. Then this guy can generate 3 neutrons, and this guy can generate 3 neutrons, and this guy, and then this guy, and then this guy, and then this guy. And you've heard of a chain reaction. And that's what happens in a nuclear power plant, is you get a chain reaction, is that 1 creates 3, and those 3 create 9, those 9 create 27. And if you're not careful, it goes boom, or if you're very careful and you're trying to design a bomb, it goes boom and blows up. Now, what they do in these power plants is they have these safety systems that can absorb neutrons. So if they want it to run faster, they remove the absorbing material. If they want it to run slower, they put the absorbing material back in. Now, you have to design those safety systems well, because if they don't work, you get things like Chernobyl, which is a major disaster. But when these things are operating well, they do pretty good, except for all this waste that they produce that then has to sit at that place because no one wants the waste in their backyard. So nuclear bombs work very much the same way. As you take this little mass of stuff, which is just enough to not explode, then you blow something up just with a conventional explosive. And if you do it just well, you actually can take that solid, you compress that solid by a decent bit. And it's enough now that these guys are close together now, and that chain reaction can occur. You've now gone from what's called a subcritical to a critical piece of uranium or plutonium or whatever it is, and that chain reaction happens very quickly, releasing all the energy all at once, and it goes boom. Now, nuclear fusion is like the holy grail of clean energy. I mean, we say that the nuclear fission produces a ridiculous amount of waste and all sorts of other things. So why do we do it? Well, we do it because we know how to do it. But you're like, look, nuclear fusion is pretty darn easy looking. You take a hydrogen isotope, combine it with another hydrogen isotope. So deuterium is the 2 hydrogen, or hydrogen 2. Tritium is hydrogen 3. You take those, you combine them, you get helium, a neutron, and a ridiculous amount of energy, so much more than you get from nuclear fission, but yet we don't do this, right? The only byproduct of this reaction is helium. The neutrons are so easy to deal with. So it's helium, right? And what's helium, right? You take a helium balloon, you breathe in helium balloon, and you might talk like this. So really, the only side effect of nuclear fusion is to produce helium to make everybody sound like Elmo. So really, why don't we do this? Right? It's got no waste products. It produces a ridiculous amount of energy. It turns out you can calculate that you can get the hydrogen you need from this, from the amount of seawater that fits in a 2-story building. I mean, it's crazy. You can power the world with the amount of seawater that fits in a 2 or 3-story building. Here's why we don't do this. Because you need a temperature of 10 million degrees Celsius to get this reaction even to start. Just to start, much less to sustain it. And we have these facilities out there called the super laser at the National Ignition Facility and other ones in the world that are trying to do this. They're spending all sorts of energy trying to get fusion started. Because if we can get it started, if we can get this working, we've solved the world's energy needs. All the energy you've ever wanted, you could totally get from fusion with very, very little side effect in terms of waste and other things. But it's a hard thing. They've been working on fusion for a long time and still haven't been very successful. At the super laser at the National Ignition Facility, they did just, I think, a year or 2 ago, finally make it so that the thing produced more energy than the lasers put in, but it didn't produce more energy than the entire system to get the lasers to run put in. So they're still a long ways off. And what you say in fusion is always 30 years off. So we're 30 years off. 30 years ago, we were about 30 years off. 6 years ago, we were about 30 years off. So we'll see. Hopefully it'll happen. We spent billions and trillions of dollars on fusion throughout the world in different countries, and it hasn't happened yet. But the payoff is so big that people are willing to put that cost in. And that's about a lot about science is the payoff worth the input? And this one it is. Even if we spend all these billions of dollars, the payoff, if we get it, is so great that it's worth the risk. But that's always a weight you have to make in science. Is the payoff worth the risk that you have to take in order to get there? Well, thanks so much for listening. I hope you had a wonderful time listening to some interesting information about fusion and fission and naturally occurring radioactive particles. And that's the end of this particular class. And I know if you're just watching this video randomly, that means nothing to you. But thank you so much for listening. Thank you for being a part of the class. And I wish you well. Bye-bye.